So we're still in Chapter 1, talking about equations and inequalities. And Section 1.3, we're going to add complex numbers to the party and look at quadratic equations in the complex number system. So we're going to add, subtract, multiply, and divide complex numbers. So hopefully that will be just a quick review for you. And then we're going to solve quadratic equations in the complex number system. So again, preparing for this section, if you need some refresher on the different kinds of numbers, that's in section R.1, and rationalizing denominators is a skill that you need to make sure you have refreshed. So we need some definitions as usual when we get started. So we're going to talk about the imaginary unit, which we denote by the lowercase letter I. And it's the number whose square is -1. In other words, I squared equals -1. So this is one definition of it. You might also have seen the definition that I equals the square root of -1. These are equivalent definitions. So complex numbers are numbers of the form, and this form, again, is important, A plus BI, where the A and the B are real numbers, and the real number A is called, surprisingly, the real part of the number A plus BI, and the real number B is called the imaginary part of A plus BI. And I is the imaginary unit, as defined above. Okay, so here's a think about it question that we'll talk about in class, but I want you to start thinking about it already. Is every real number a complex number? And we'll talk about that. So let's go on to objective 1, where we're going to add, subtract, multiply, and divide complex numbers. So first we're going to talk about the property of equality of complex numbers. A plus BI equals C plus DI if and only if A equals C and B equals D. So in math we use the words and or, and we make a distinction between what they mean. So in this case it's and. You have to have both. The real parts have to match and the imaginary parts have to match up. Then if you're adding complex numbers, you add the real parts and you add the imaginary parts. So you can think of this as similar to combining like terms where you have constants and say coefficients on I, if you want to think of it that way to see how it matches up to what you already know about algebra. Then if we have a difference of complex numbers, you do the difference of the real parts plus the difference of the imaginary parts times the I. So we'll do a little practice in class, do this example. The product of complex numbers, it works a lot like foiling. So you need to do A times C plus ADI plus BCI plus BDI squared. Well, you never leave I squared in your answer. So you can have AC plus ADI plus BCI plus BD times I squared is -1. So if I combine the real part, you'll see I have AC minus BD plus the quantity AD plus BC times the I. So we'll do this example together in class. And now let's talk about some notation if Z, which is very commonly used to represent an arbitrary complex number. So if Z equals A plus BI is a complex number, then its conjugate, and it's denoted by z with a bar over it. So you read this z bar. Z bar equals, put a bar over the a plus bi, and what that means is a minus bi. So whatever number was multiplying the I now is opposite, but the real part doesn't change. So what happens when you multiply a complex number by its conjugate? Let's see, we'll get negative 6 times negative 6 is positive 36. Negative 6 times negative I is plus 6i. I times negative 6 is minus 6i. And then I have minus I squared. So these guys will cancel, and I have 36 minus negative 1, which is real. So when you multiply a complex number by its conjugate, you get a real number only. We'll do it in general together in class. So if you do it with letters and show what happens, then you can say that always happens. Okay, so we have a theorem here. The product of a complex number and its conjugate is a real number. And if z equals a plus bi, then z times z bar equals a squared plus b squared. So you can see that that's always true. Okay, so now let's look at the quotient. That's a little different than some of the other operations we've been doing, which seem kind of intuitive. To find the quotient of complex numbers, the way you do it is to multiply the numerator and denominator by the conjugate of the denominator. So hopefully this is familiar. So we'll do this one together in class. And let's look at these little theorems here that says, the conjugate of a real number is, a real number, because it doesn't have an imaginary part. So it's just a. So if I do the conjugate of a, it's still going to be a. It doesn't have an imaginary part. So symbolically, you'd say a bar equals a if it's a real number only. So the conjugate of the sum of two complex numbers equals the conjugate, the conjugate of the sum equals the sum of the conjugate. So the conjugate of the sum equals the sum of the conjugate. So what we say is the conjugate of the sum, so we have two complex numbers, z plus w, and we want to do the conjugate of the sum. Well, it turns out it's the sum of the conjugates. So you can do the conjugates first and then add, or add first and then do the conjugate. And if you play with this a little bit, you'll see that it works. So if you do 2 plus 3i plus 4 minus 5i, and you say do the conjugate of that. So you're first going to go 6 minus 2i. What's the conjugate of that? 6 plus 2i. Well, then if you do the conjugate of each one separately, you'll see that that's 2 minus 3i plus 4 plus 5i. So sure enough, we get 6 plus 2i. So you can prove that to yourself. I'm just showing you a specific example. And the conjugate of the product of two complex numbers equals the product of the conjugates. So if I have z times w and I do the conjugate of that, turns out that's the same thing as if I do the conjugates first and then multiply together. And again, we could prove that to ourselves. So this goes up here, sorry. So powers of I, they follow a pattern, and I want to do that in class together so that we look for the pattern together. And then let's look at objective 2, where we're solving quadratic equations. In the complex number system. So if capital N is a positive real number we define the principal square root of the opposite of that positive number. And so we write that with symbolic language as square root of negative n. So now we're doing the square root of a negative number. And we say by definition that the square root of negative n equals square root of n times I, and make sure it's clear that the I is not under the square root. And so you can also write it in the front, and we often do, to make it crystal clear that the I is not under the radical. So I is the imaginary unit where I squared equals -1. So square root of -9 is going to be square root of 9 times I, but we know the square root of 9 is 3. So this is saying that you never work with negatives under the square root. You always turn it into a number with an I. So in the complex number system, the solutions of the quadratic equation ax squared plus bx plus c equals 0, where a and b and c are real numbers again, and a is not 0, so that it actually is quadratic, are given by this formula: x equals the opposite of b plus or minus square root of b squared minus 4ac all over 2a. And we'll do some practice of solving equations in the complex number system. And in fact, we'll talk about number 74 because that's an important quadratic in form, which we'll look at lots more of those later. And that's all we have for today.